In today's video, we'll be diving into an important concept used in various areas of electrical engineering, the stray capacitance matrix. Stick around till the end. Let's start by imagining a simple capacitor. The capacitance value is C. We have a positive charge here, plus Q, on one plate and a negative charge, minus Q, on the other plate. And we know the relationship between the charge Q, capacitance C, and the voltage difference between capacitor plates, or more specifically, C multiplied by V plus minus V minus, where V plus is the voltage of this plate, the voltage on the positive side, and V minus is the voltage on the negative side of the capacitor. Let's expand this idea. Suppose we have three conductors and a ground surface. This setup is often seen in power engineering, and it's a great example of how to calculate the stray capacitance matrix. I'll call these conductors 1, 2, and 3, and I'll call my ground 0. Between any two conductors, a capacitance can be defined. I'll call it a stray capacitance or parasitic capacitance. Therefore, for example, between conductor 1 and 3, there is a capacitance. I call it C13. There is another one here, which is called C12. And there is a capacitance between conductor 2 and 3. I call it C23. Also, each conductor has a capacitance to infinity or ground. Therefore, there is a capacitance here, partial capacitance between conductor 1 and ground. I call it C10. Here we have C20. And between conductor 3 and ground we have C30. What you see is the partial capacitance diagram for our system. We have here three conductors plus a ground or infinity, and we have 6 different partial capacitances in here. Now let's focus on conductor 1. Imagine a closed surface around conductor 1. The total charge on conductor 1 is the sum of the charges stored across all its capacitances. Therefore, I can write that Q1 equals Q12 plus Q13 plus Q10. For example, Q13 is the charge stored on the capacitance C13. Now let's use our initial formula here. We know that the amount of a charge stored in a capacitor equals its capacitance multiplied by the voltage difference. Therefore, I can come here and write these three equations. Q12 equals C12, its capacitance, multiplied by the voltage difference. One side is connected to V1, the voltage of first conductor, and the other side is connected to conductor 2. And we can do the same for the others. Q13 equals C13 multiplied by V1 minus V3, and Q10 equals C10 multiplied by V1 minus 0, because the ground has the 0 potential, and this equals C10 multiplied by V1. Let's sum up our equation again. Q1 equals... Okay, let's reorder this equation with respect to the voltages. I can write it here. Q1 equals V1 multiplied by. Let's see, we have a V1 here, therefore we have a C12 here, C12. We have a V1 here, therefore plus C13. We have a V1 here, plus C10. Plus V2 multiplied by, we have only one V2 here and it has a minus sign, therefore it comes here minus C12, plus V3 multiplied by, we have only here only one V3 with minus sign, therefore it comes here minus C12. We can do the same for conductor 2 and conductor 3. I'll do it very fast without speaking, you just follow the lead. I'll keep the order put V1 here, then V2, then V3. And doing this for the third conductor leads to these equations. We now have our three equations here. First one, this is the second one, and this is the third one. We can combine all these three equations into a matrix form. At the left side we have Q1, Q2, Q3, therefore at the right side we have a capacitance multiplied by, we have common V1, V2 and V3 in all of our equations. Let's write it down our coefficients. Here Q1 equals V1 multiplied by this parenthesis. I just move it here. Here we have this one. And in this position we have this one, the coefficient of Q3 versus V3. And now the off-diagonal elements, Q1, V2, that's here, minus C12, here is minus C13, this is minus C21, here we have minus C23, and the last row we have minus C31 and minus C32. This is the stray capacitance matrix in its full glory. It's the mathematical representation of the relationship between the charges on each conductor in our system and the voltages applied to them. A few things to note about this matrix. First one is the symmetry. The matrix is symmetrical, which means, for example, C12 equals C21. These are essentially the same capacitance, just seen from different conductor pairs. This is C12 and at the same time C21. Now notice the second property. Look at the diagonal elements on this matrix. All are positive, while the non-diagonal elements are all negative. And the last but not least, if you add up all the elements in a single row or column, you get the capacitance of a conductor to infinity or to ground. For example, if I add all the elements in here, this is my first element, second element, and the third element. These cancels out and these add up to C10, which is the capacitance of the conductor 1 to the ground. As the final point, for a single capacitor, you have seen that we have equation very simple, that Q equals C multiplied by V. For a system of capacitors, we have the same equation as you can see here, but in a matrix form. The matrix of Q equals the matrix of capacitance, Maxwell capacitance matrix, multiplied by the matrix of conductor voltages. Alright, that's a wrap for the theory behind the stray capacitance matrix. If you want to see how to export this matrix from console, I've covered it in another video, so be sure to check that one out. In that video, you will see exactly how to extract the matrix. Just take a look at the screenshot of the software output, where you can see the diagonal elements are positive and the off-diagonal elements are negative. Also stay tuned, because in my next video I'll show you how to use the Maxwell capacitance matrix to solve a simple circuit problem. It will be a great follow-up, so don't forget to watch that. If you enjoyed this video and found it helpful, don't forget to subscribe, like and click the bell icon so you'll never miss a new tutorial. I'll see you in the next video. Till later.